Hello FTC Alberta. You hear my voice, you see this title screen, it probably means it's time to talk about a week of subsystem design and things for the game climbing high. Looking forward to this one. So we've actually got 5 teams, I believe 5 teams that have submitted something up to this point, so I want to talk about a few of the designs. I want to pour a little bit of mentor feedback into them and we can definitely go from there. So the one that I have on screen this very nice X-Drive robot that we're going to break down a little bit here. Now, I'm going to show you just a quick pan around of this because this is a basic Tetrix robot, and there's a couple things that I would do a little bit differently on this one. I'll tell you what they are, but I'm actually going to show you because we had some feedback go to the Mandela teams about this exact same thing. So we're actually going to talk about theirs because I'm going to hop over to their version of the X-Drive. And I got to give the guys heck because they didn't follow our branding guide. That's totally not our blue. That's like a teal blue, or more like a Carolina blue, maybe a darker gray Carolina blue. But I digress. For 14.717, 15.259, they've laid out their own versions of the X-Drive. And as you can see, that they're very similar to that one that Steam has done. And that actually is not a bad thing. But I'm going to walk through why these are going to be a little bit easier to work with. They've actually put on a either laser cut or 3D printed base plate on here. And what this is going to do is actually square the frame out. And you can see that the team has actually put in a couple different versions of here for different sizes. Because we may find as we go through this challenge that we want different sizes. That squaring out of the frame is something that's really important. We found that this season when we played with an X-Drive, that this frame tended to not maintain its square if it wasn't supported by some cross beams or a flat plate of some sort to hold it all together. That being said, very strong design. I also want to point out on the X-Drive, this design uses single Omni wheels on all 4 corners. That's really good if you're trying to cut your weight down. One of the things that the advantage of having a double Omni wheel is that it actually allows you to have some redundancy. We've broken Omni wheels in the past. The bases of them are they're built in nylon, and if they take a hit, which in robotics competition, your robot sometimes takes a hit, having one of those rollers break off of there isn't as catastrophic if you've doubled them up. It is twice as expensive, it is twice as heavy, and if those are design constraints that you're building around, that's fantastic. I also want to point out that the rationale here is actually really good to have at each stage of the subsystem game. If you actually post these and you actually talk about these, it actually goes a long way. And I mean, they've also pointed out last season what we did. I mean, last season we did this, here's how it worked, here's how it didn't. We know how to make it work from a prototyping and building phase. There's some merit to that for sure. I note that on this one, this robot here is 18 inches by 18 inches, and 14715 Peter Lougheed School actually ran this exact same drivetrain last year quite successfully, and it is something that can absolutely work for you. Just keep in mind when you're trying to get up on that top step, it's harder to get this frame on top of the step because it's the exact same size. Now, if you're not going for the step, no problems at all. And again, this is what the Mandela teams have designed for, is the idea that you could have a robot that's 13 inches by 13 inches, still fitted in an X-Drive, and still probably be fairly competitive. Now once we cut through there, and I suppose I should show these wonderful logo pieces, on the way through the next group that we are going to look at, I believe, design, and this is I believe uses the GoBuilda chassis. Now I want everyone to look here because this is really neat. If you're building with GoBuilda, which is one of our new platforms that some of our teams in Alberta haven't used as frequently, it looks at things a little bit differently. You'll notice that the bars look a lot like a Tetrix bar. They're that C channel, they're still pretty beefy. They're actually a little bit bigger than the Tetrix bar, and they actually use plates on the inside of them to support a lot of the stuff. And in this case, we've actually used a plate to support our DC motor here. GoBuilda has their own version of them. I believe they're called the Yellow Jacket. They're actually very sharp DC motors. We may talk about them in a future video, as well as bevel gears. Now here's how a bevel gear works. Bevel gear is going to allow you to transfer motion at a 90-degree angle. So this bevel gear can spin, and it'll spin the actual drive axle. Now, I don't recommend bevel gears for somebody who's a new team, but if you were an established team, this is something you can definitely explore because as you can see in the form factor here, it allows you to hide all of the motors directly in your frame. You don't have to put anything in the middle, so you have a lot of space for mechanisms, which is super cool. Now the drawback is those bevel gears provide another level of complexity and potentially another point of failure. If you have one of those go down in a competition, they can be kind of finicky to get fixed in the middle of a contest. that's something your team has to look at and actually has to figure out what they want to do. Do you prefer the simplicity of having, say, a direct mounted motor on an axle, which has its own challenges, such as the Indigestem team here, where these can actually bend if they're put under the wrong force? Or do you go for something a little more complex that gives you a better form factor? There's no right answer here. It depends how your team wants to actually look at the challenge. For our next team, on actually putting together both a 3D model and a 2D drawing of this. This isometric and orthographic view of this robot is actually super useful as an overview, and I do recommend that teams do this for their subsystems, because when showing things off, it really helps in your engineering notebook if you can show off the designs you went throughout a build season. It goes a long way when the judges look at that sort of thing and say, well, here's kind of where we went from start to finish. Now let's break down their robot. And I have to make an assumption here. I didn't ask this because they use the Rev frame for most of theirs, but they actually have these what look like 3D printed bumpers. I'm really happy. This looks like an FRC robot. It makes me very pleased here on the sides. I'm going to assume that those are made out of some kind of polycarbonate or some sort of plastic, or potentially 3D printed. Now, I'm going to show you a cool thing about this robot. This robot actually uses a completely different drive style than what we've used prior, in that it uses DC motors attached with tooth belt. Now, usually when we see an FTC robot, we are direct driven. We've seen some versions that are chain and sprocket driven. This belt drive is actually another way you can do it. And there's some advantages and disadvantages. The actual amount of force transmitted through this belt under normal load is about the same as a chain. But the difference is when you resist a belt, what's going to happen is the belt is going to slip instead of actually grabbing. If you put too much torque on a chain and it is stopped, let's say the wheel gets stuck, there's a piece of debris jammed in it, or it just can't move, the chain will break. Or if you're lucky, the chain will break at your master link, and if you're unlucky, something else in the system will break. This actually introduces a potential failure point on purpose, and what that means is that belt drive will slip instead of breaking, which means you save your robot. And as long as it's something temporary, like I say, a game piece getting stuck in the wheel or under the chassis, that's actually a really good thing to have. And it also allows you to transmit this force and potentially change the actual center of gravity of this robot as well. This is actually one of the robots, I'd say, with the highest center of gravity here, but with this kind of design, there's nothing stopping you from playing around with that and messing around with it and moving it all over the place. And yeah, center of gravity is going to matter a lot for this particular challenge. Our last one here, we're going to talk about Team 40. That we looked at, and it was in Onshape, so I'm going to apologize while I fumble my way through the view cube in Onshape, which is not my favorite thing, but that's okay. So I want to walk through what they've actually done, because this is a very cool design. What you notice immediately on the bottom is that there's actually 8 wheels on this robot, and in a really weird setup in the sense that there's mechanisms on the outside and there's grip wheels on the inside. Now, when you look at this machine, you have to notice a few things, because this machine is actually made to have either grip wheels and move very quickly across the floor or with traction, or to swerve with mechanism. And there's a bunch of different ways to do this, but I love how 4042 has actually looked at this, because they've used a rocker system. I'm going to move myself off to the side here and I'm going to show you, because right now their near side drive rail, the one closest to us, is set to be on the mechanism wheels. You can see them here at the front and the back. The far side rocker is set to be on the grip wheels. They are set down right now on this particular chassis. Now, how does this all work? Because this is a very cool mechanism. If we look on each side here, what we actually have are these rockers are actually mounted at a central axle around the mechanism wheel. They are pivoted so that this grip wheel could actually rotate itself up into the frame. This is then in turn attached to the other rocker, and I'm just going to zoom in because it actually helps to kind of visualize this. These rockers are actually attached together using a rotating pivot plate. That allows the whole thing to move in unison downwards and upwards so that you always have the same level of contact with the wheels. And it is all kind of actuated by a servo here. We've got one on each side, and the servo itself, spin back, actually attaches to a rotating bar. That rotating bar is attached to a coupler of some sort that would then be attached to this other coupler, allowing this servo to lift the entire mechanism of rockers up and out of the frame, so they could lift up to drive on the mechanisms, or they could shift down to drive on the actual grip wheels. The other cool piece they've done is they've actually got, just like we talked about, they've got their motors sitting in their drive rails using the Go Build a System with the bevel gears, and it's then chained onto the actual wheel system. Now, since there's not a lot of rocking going on with the mecanum wheel here, we can see that we've got our actual sprocket here. We got our sprocket on our drive motor and our bevel gear here that runs onto our sprocket on our mecanum wheel. This could then, from there, very easily transmit force onto our other wheels, which could also be driven by something else. This, all in all, is an incredibly ambitious project, and I want to say congratulations to 4042. This is one of those really advanced pieces of CAD, so very well done. Now, that being said, one thing as a mentor that I would advise a team looking at this to do is, have you done something similar in complexity to this before? Have you tested something like this in an off-season? Off-seasons are powerful. Doing something during the summer like this will tell you if your team is capable of doing this consistently. Because one of the problems you run into when you add this much complexity in a build season is that you do add more points of failure. This drivetrain, while it is four-wheel drive and has 4 motors attached to 4 different wheels, it does have the potential that if part of this servo mechanism were to fail, you would actually potentially lose one of your drive rails, thus making it so you couldn't play the game very effectively. Likewise, you do have force transmitted from a motor through a gear, through a sprocket, through another sprocket. Again, more failure points are something that teams fight with, and the elite teams do these things really well. And if you're at that level and you're going to put in that time and effort and you're going to thread locker all of your screws and make sure nothing can vibrate loose, you will be one of those elite teams. And I look forward to seeing if this could actually get put together and how it would work, how it would function, and how it would move. Now, you've all got a challenge. I will put another video with some other CAD notes and things about Fusion here in the next day or two, but your task for the next week is to design one more subsystem. Realistically, your drive base is usually the first subsystem you look at. You have to drive around the field, unless you're playing Ultimate Ascent. Anyone wants to look up that FRC game, there were definitely some static robots with no wheels on them during that one, but for the most part, you're going to go and build a drivetrain first. But now I want you to look at the second piece. For some teams, that's going to be a climber. It's how do you get onto one of the podiums. For some teams, this is actually going to be a time to look at how you're going to project the game ball into the target. Good luck. I wish you luck. Check any questions you have on the Discord, and enjoy the rest of the week.